UK right after. Right
2014.
After 14. All
yeah.
Right, yeah. And you were somewhere else before that, right? Sorry.
I was at Carlos III, University of Carlos III.
Okay. That's
yeah,
right.
for 6-7 years. Yeah. So should I upload the slides? I guess.
I guess so. And I'm looking for Alex's here. So we're now live.
So I think you can see them, right?
I can see your slides perfectly. Thanks.
Okay, so maybe put them. I'm not sure if I can put them full screen. Yeah. Anyway, it's good to see you. So
yeah, same here.
I see Rustam around. So hi, Rustam.
Hi, Abderrahim.
Good to see you. Yeah. So.
All right, let me just say a few words.
Okay.
Very good to see you and welcome everyone to another of our center's seminars. Exceptionally good to see again after a long while Professor Taamouti, who is now at Durham but is living for Liverpool, as I'm told, and he will talk on ValueatRisk and the measurement error. Abderrahim, if you want questions, we can either ask them during your talk or wait until the end, up to you.
Fantastic. Either way is fine with me.
Yeah. And we usually have about an hour.
Fantastic. Great. So thank you very much for inviting me. So it's a great pleasure to see you guys and also present my research here. So I'm going to talk about value at risk and their measurement error, and this is a joint work with Mohamed Doukali and Xiao Zhongsong. Okay, so I'm gonna outline a bit my presentation, and then I will go with the details later. So I'm gonna start with the motivation. So motivating a bit why we need the techniques or the technology that I'm presenting here, and just in case I don't control my time, so I'm gonna summarize the results so you can have at least an idea of about what I'm doing here, and then I will explain a bit the framework that I'm gonna use to derive the distribution function of latent true portfolio return. So because the idea here is to estimate the value at risk of let's say a portfolio of stocks that are measured with some errors. And so what we're gonna do here, so as you know, the value at risk is a quantile measure of risk. So one way to estimate that is if you have the distribution function, you can invert it and then you get the quantile. So the idea here is to we're gonna be after the calculation of distribution function for the latent true portfolio returns. So using the observed returns and some other assumptions, and so once we have that, we use that to calculate the value at risk, and then later on I will show you some Monte Carlo simulations where we look at the performance of our method. So in particular, because we are interested here in estimating the value at risk, so we will be looking at, for example, things like bias, the variance of the estimator, and or in general the mean square error. And then I will finish with an empirical application where we use this technique for the estimation of value at risk for some active stocks or stock market returns. Right. So the motivation. So this is as I said, is about value at risk. So estimation of value at risk. And we know that this measure is quite widely used technique to measure risk of loss for investment, so individual investment. I should possibly mention that this technique that we introduce here can be also applied to expected shortfall. So that's something that we work on now. So we also extend these results to estimate the expected shortfall, which is another measure of risk. But value at risk is, as I said, is a quantile. It's just a measure. It's like a quantile measure that measures the worst expected loss over a given horizon. So typically the banks or financial institutions, they take a day or week. So they calculate this every day or week at a given statistical coverage rate. So typically they take 1%, 5%, or 10%. And of course, this is a quite important measure because it's a way for banks, for example, to know how much capital they should put aside to protect protect, for example, our saving in banks. So that's why for financial managers and also for regulators, this is this is a quite important. It's quite important to have a precise estimator of value at risk. And this estimation, as we show a little bit here, and of course we deal with it here. So this estimation can be affected by the presence of measurement errors. So measurement errors in the general sense, not only market microstructure noise, but that could include other causes like non-synchronous trading, rounding errors, infrequent trading, etc. So that's the motivation. So how we do that? So here we we develop our methodology here in the context using or considering an additive measurement error model. So as you know, this is a quite usual model that we consider in finance. So those of you who are familiar with the literature on volatility, for example, using in how to estimate volatility using high frequency data. So we know that this is what is used in the finance literature. So an additive measurement error where the observed return or stock return is nothing else than the true latent stock return, and we add to it some contamination or some measurement error. So the observed return is observed with the contamination or with the measurement error. And as I just said, so using this model, I mean, if you look at in finance literature, so there's a huge literature on that investigates the impact of contamination and in particular microstructure noise on the estimation of volatility. So, to cite few papers from a large literature. So I'm mentioning here Aitzahalia and co-authors and Bendy and co-authors. However, no attention is paid to the effect of measurement error on the value at risk estimation. So thus there's no robust estimation technique that can help us deal with the presence of measurement errors in the stock prices. So I mean, this is a bit let's say simulation exercise or illustration to show a bit what happened when we ignore the measurement error. So what I'm showing here is the right tail of distribution, but I mean, because here I'm assuming symmetric distribution, so you can see similar thing from the left hand side, which is which can correspond to the risk. So here what we see is a tail of convolution of normal and student distribution, but you can do that with other distributions. So what we have, so the solid line here is the let's say the true return, and sorry, is the observed return. And this line here, sorry, it's not very visible here, but this is the true latent return. Okay, so the true latent return is here corresponds to let's say simulated from student t distribution with 3 degrees of freedom, and then we have the measurement error down here, which is from normal or standard normal density. So the convolution of these two, so what you get here is this observed return that is in between. So what we see here is that the tail of the latent, let's say the latent return, it dominates the one of the observed return. So what that means in terms of risk management is that if you just focus on the observed return to estimate your value at risk, then you will end up underestimating the risk. So because this one here corresponds to much more, let's say, fat-tailed than this one. So that's what I'm summarizing here. So the right tail of the density of the latent return dominates the right tail of the density of the observed return, and you can see similar thing from the left-hand side. And but the existing estimator of value at risk, they ignore this. They ignore the presence of measurement error, and so that could lead to inconsistent and also underestimation of risk. Hence, hence the motivation of this paper is to provide a robust estimator method that can deal with the measurement error. So let me summarize the contribution just to make sure that I'm not in case if I miss my time here. So so what we do, we develop a semi-parametric estimation approach for value at risk when the stock prices are contaminated with the measurement error. Derivation of robust estimator of value at risk is first made under. So what we do here, we need to make some assumptions, as you will see in a minute, on the distribution of the measurement error. So in a step one, we develop our estimator, or we derive our estimator under the assumption that the distribution of the noise or the measurement error is known. And then we relax this assumption. But so what we do, we assume that the noise is normally distributed, which is quite standard assumption in the literature. So assuming that the macrostructure noise is normal, but we consider that that its variance is unknown, and then we show how to estimate that. I should possibly mention here that related to the previous point. So assuming the normality of the error term will not affect the distribution of the I mean, assuming that the measurement error is normal, doesn't exclude having the stock returns, the true stock returns, non-normal. Because I'm mentioning this because we know that the stock returns are not normal according to the empirical work. So that's just to say that you can still allow for any type of you can still consider non-normality for stock returns.
How about the form of that measurement error being additive as opposed to, if you think about this as a financial return measurement error and the likelihood of manipulation, for example, clearly depends. The higher the returns, the more, I guess, whether this is an additive structure or some sort of scaling multiplicative structure is a question.
You mean about this one, right?
Yeah.
Yeah, okay. So the calculation, as we will see under this assumption here, they are quite straightforward. Now, I guess your question, if we relax this and we consider maybe more general structures, I think that will also, that will certainly, complicate the calculation. But we didn't try, to check how complicated they will be, the calculation. What I can say, maybe, okay, but that's not really related. But the calculation we did here is under normality of the measurement error. You can, in a very straightforward way, you can relax that assumption. You can consider any distribution of the error term and you do the calculation. But for the functional form, this here, we didn't try, to go more general. But I think there is some literature, that discuss this, this type of assumptions. I think what's her name? Susanna. She's at Brown University. She's very famous on. She's one of the leading researcher on the estimation under the measurement error. I think she has a couple of chapters in books where she discusses this type of alternatives. But honestly, we didn't try to see how we can fit this here. In terms of calculation and yeah. Right. So yeah, and then yeah. So then then the next we do is to so we have a Monte Carlo simulation exercise where we examine the performance of our approach, and we also compare that to some to a non-parametric estimation of value at risk that ignore the measurement errors. So I'm talking about the simple empirical the value at risk that is calculated using the empirical distribution. And then at the end, I'm going to apply this to estimate value at risk for 5 international market indices. So the framework. So here we consider that we have we consider an economy with n risky assets. So we have the vector of the observed log prices for the n assets at time t, and then we define also the vector, with the stars of latent true log prices at time t. So what we assume here is that so we consider that the price, the observed price, is contaminated, so is the true price plus measurement error. That is IAD with some variance, and then we assume for our calculations here, we assume that the noise or the measurement error is independent of the unobserved prices. And as I said, in a first step, we assume that the density of the measurement error, which we denote f epsilon, is known, and it follows a normal 0 sigma. So sigma is known here, but as we will, as I will show later, we're going to relax this assumption. But again, as I just mentioned, you don't need, you can redo the calculations here for other distributions other than the normal ones. So all what you need, if you have an expression for the characteristic function of the error of the measurement error, that will help. That will help you. You can use that to derive to do the same calculation, similar calculation to what we did here. So it's all what I'm saying is that this assumption here of normality is not really restrictive. So if all what you need is an expression for the characteristic function of the measurement error. And now what I'm going to do, so I'm going to, instead of working with prices, I'm going to work with the returns. So you can do a little transformation on this, and then you can convert, this expression here in terms of returns. So, the return, the observed return is contaminated. So it's equal to the true latent return plus a noise. So the noise now here, or the measurement error, is now the double of its variance is the double of the variance of the noise in the price. And this is, again, this remark is what I said before. So it's normality of the measurement error is not restrictive. So it doesn't exclude non-normality of the returns. And now, because we work with the portfolio, so we do the calculation here for a portfolio, and we look at the portfolio of the value at risk of a portfolio. So here we consider a linear portfolio with the return that is given by this expression here, where W is the weight, is the known vector of portfolio weights. And then in a similar way as we did for the individual returns, you can show that the portfolio return is contaminated and is equal to the latent portfolio return plus a measurement error. And this measurement error is just the weighted, if you want, the weighted, the sum of the weighted measurement errors of the individual returns, or the returns of individual stocks. Now I'm going to move so to the how we calculate the distribution of the latent true portfolio return. So it's quite easy to see from simple to see from equation 3 because of the independence here between these two terms, that using Fourier transformation you can write the characteristic function of the observed portfolio return as a product of the characteristic function of the latent portfolio return and the characteristic function of the measurement error in the portfolio return. And then if you know the density of the measurement error, that will allow you to get from this you can get in fact either the density or the characteristic function of the measurement error in the portfolio So in this case, for example, the characteristic function, it's quite easy to see that is given by this expression. And under the normality, it simplifies to this. So under the normality of the measurement errors, it simplifies to this. That's for, so what we do, so we try to isolate this. So we are after this. So if we have the characteristic function of the latent observed portfolio return, so we are after this one. So if you have this and this, we can get this. So, so that's what we just got this guy here. And for this one, we go non-parametric. So so the characteristic function of the observed portfolio return can be estimated using, for example, empirical analog, as we show here. But you can consider other estimators. I mean, we didn't investigate this, but you can use a sort of like, a kernel-based estimators of characteristic function or any other non-parametric estimator of the characteristic function. But here we go simple with the empirical characteristic function. And then, of course, once we have these two terms, then we can use them to have an estimator of the characteristic function of latent true portfolio, as we show here. So combining these two terms, that gives you this expression. Then, of course, the issue with this expression is that is not integrable. So we had to, smooth this expression using some kernel functions. So as we do here, so we use a Fourier transform of some kernel function. And for this, we are inspired from these two these two papers. And again, following these guys, we consider this type of kernel function. And then now, once we have the characteristic function, then we can use it, as you know, to, or invert it to get the probability distribution function of the target here, which is the latent true portfolio return. So using Gill and Pillai's 1951, we have this expression of the probability distribution of the latent portfolio return in terms of its characteristic function here. And then once we replace this expression here as is given here or here after smoothing, then you get this expression that you can write in the following form, like in terms of kernel, sum of kernels. So this is what we call deconvolution kernel. Well, that depends on some bandwidth parameter. Yeah, so we're gonna have to work with this one. Now, for the value at risk estimation, again under the measurement error. So what we're gonna do, we're gonna inverse again the distribution function. So now in terms of expression of value at risk, so if we are interested in value at risk at, let's say, nominal coverage rate alpha, that we denote by this, and let's consider that is a positive quantity, then all what we have is to replace this guy by the value at risk minus. So because we look at the negative side, so we go with minus value at risk. And then we get this expression. So this expression of the cumulative distribution or the probability distribution of the latent portfolio return that depends on the value at risk. If, expression here, okay. So now, yeah, so to calculate the value at risk, the probability term here at the left-hand side has to be equal to alpha. So if you are interested in estimating the value at risk at nominal coverage rate alpha, then all what you have is to replace this guy by alpha, and then you will have an equation that depends on value at risk and that you can use to solve for value at risk. That's more or less what we do here. So yeah, so value at risk can then be calculated by inverting the distribution function, and then as I just expressed. So if you are interested in alpha value at risk, alpha percent value at risk, you replace this by alpha, and then you can rewrite a little bit the terms here, and then you get this equation. So that's an equation that depends on the value at risk. So now. Unfortunately, getting an analytical expression in general cases for value at risk by solving this equation is not possible. So what that means is we are forced to use numerical solution to obtain or to estimate the value at risk here. So that's what that's what we can do by solving this equation here. Or if you want, if you prefer to work with some quadratic form, so you can just take the square of this term and you minimize it. So that's what I express here. So the value at risk will be a minimization solution, or the solution that that corresponds to minimizing this quadratic form. And however, we again face an issue here. So that's we can do it numerically, but the problem is that we have this integral that again is difficult to assess in practice. And so what we're gonna do, so we will have to use some, truncation. But before that, so what I mean, there are different approach to deal with this here. So several years ago, I wrote a paper on value at risk, on estimation of value, analytical estimation of value at risk in the context of Markov switching models. If you look at that paper, I suggested a different way of dealing with this integral than the one that I'm using here. So what we do here, we use what we know as a series representation. So like writing this expression exponential and sine in terms of polynomial expression or sums, and so that's what we do here. So if you do that, then this term here is given again by this term here. And but again, we still we didn't solve again the solution. We didn't solve again the problem here, because we still have an infinite sum. So the way we deal with this is we truncate. So that's this expression here can be written as two terms. So one that is truncated term, and one that we call like a reminder, or like a remaining term. Yeah, so that's how we do the the implementation of this in practice. But again, the question, of course, here is what should be these truncation terms? I mean, L and K. So should we stop at 1 or 2, 5, 10? So we try to investigate a bit this theoretically. So we try to like see if we can find L and K for some tolerance errors. So let's say I say, okay, I want this term here to be like 10 power minus 10. Sorry, 10 power minus 10 or something like that. So we try to see whether we can, by fixing this level of error, whether we can find analytically L and K. We were not able. I mean, we didn't manage. I mean, we didn't push very hard, but we didn't. It was not that straightforward. So anyway, what we did is, this remaining term, you can decompose it to 3 terms. So this term, K and L and the double sum of infinite. So what we show is that these 3 terms can be bounded in the following way, but we couldn't manage, like to as I said, like fixing some levels of measure let's say tolerance errors, and then invert this equation to get a K and L. So we couldn't manage that. So anyway, at the end, we were forced to do that by simulation. So so that's what I'm saying here. So how large should L and K be in practice to make the remaining term negligible? It's a question that we investigated intensively by simulation. So what we find is that taking, for example, L equal to K equal to 10 yields two satisfactory results. Sorry. So satisfactory result in terms of bias and the variance and the mean square error of the estimator. Now let me move to the again. So remember, I made an assumption that that the error term is normally distributed with some known variance. Of course, in practice, that's that's a very complicated assumption. I mean, it's hard to accept that assumption. I mean, to say that we know the variance of the measurement error. But again, as I mentioned before, the normality is not an issue because again, you can ask if you have the characteristic, as I said before, if you have the characteristic function of the measurement error, either normal or non-normal. So you have its expression. You can again use this formula and do this derivation. So normality is not a big issue here. But yeah, so now when we relax the assumption of the known variance in the context of normality, apparently there are some estimators in the literature. So you can find that in Itzahelia and Quarters 2005 that can help estimate the variance of the measurement error. And that's given by the following expression here. So you can use the prices, the observed prices, to do so. Now I'm going to move. I think I'm not controlling my time. Sorry. So I still have around 20 minutes, right?
Yeah, 20, 25 minutes.
Okay, good. So I think
can I
yes.
ask you something
Sure.
regarding that estimation of the previous slide?
Yeah.
So the variance here is that's quite important, right? So assuming the distribution, the variance is what's going to drive this deconvolution, and effectively the estimate of the true VAR.
Yeah.
Because this is the only thing that affects the identification of the deconvoluted component, right? The distribution.
Yeah.
So what assumptions would 9 make on the measurement error, besides normality? That is what that are of substance here.
Yeah, I mean, you know, so yeah, I mean, as I said, is you also need the independence. I mean, sorry, you need IID. So that's another. I mean, I would say another essential assumption here. But of course, I mean, honestly, we didn't try, but. I mean, this is quite, you know, I think in the finance literature is quite standard. I think at least what we saw in many papers, they assume IID, but certainly maybe there are some extensions. I mean, people assuming some sort of form of dependence. I believe we can redo the calculation here, relaxing the assumption of IID of the measurement error. I think the calculation will be possibly, you know, less complicated under some, you know, type of under some type of independence. Yeah. Right. So now I'm going to move to the Monte Carlo simulation. I think I have you know, maybe some time for this. So the Monte Carlo simulation. So I think we did the quite extensive exercise here. So to summarize a bit. So what we do in a first exercise, we look at how our estimator that adjusts for measurement error compares in terms of bias, variance, and the mean square error of the estimator with what we call an adjusted estimator. So again, an adjusted estimator, we try to be more like, you know, to go more non-parametric because we didn't want to have the influence of any parametric, you know, parametric model. So we use we use the estimate. I mean, we use the estimation of value at risk using the empirical distribution function. So as I said, we do three exercises. So in the first exercise, we compare the performance of our estimator to this unadjusted estimator, assuming that the true distribution of the measurement error is normal. Sorry. Forgot. Sorry for that. So yeah, I mean, in the first step, we assume that the data is generated from a measure. The measurement error is generated from normal 0, 1, and that's the true distribution. And then in a second step, we asked the following question. We said, how our estimator will do compared to the unadjusted one if our estimator is calculated under normality of the measurement error, but the data or the type of contamination in the data is from other distribution than normal. So we consider like student mixture. So if we get it wrong, so we assume that the measurement error is normal, but it's not, how our estimator compares to an unadjusted one. And then the third exercise, we said, what if there is no measurement errors? Can our estimator still perform well? I mean, compared, let's say, to the unadjusted one. So that's the 3 exercises. And now to like simulate the data, we consider this equation. So the portfolio, the unobserved portfolio return plus the unobserved portfolio return plus the measurement error is equal to the observed one. So again, as I said, we assume that the measurement errors is generated from N01. And then what we do, we first simulate the latent portfolio return. So using 3 different models, ER1, MA1, and GASH. And so once we have the generated latent portfolio return, plus because we can generate the errors from normal 0, so we combine that to get to simulate the observed return. And so then what we do, I mean, because we look at the bias, standard deviation, and mean square error, so what we do, we analytically calculate 1%, 5%, and 10% value at risk of the true portfolio return. So as we do here, so you can do that analytically from the type of assumption we consider, and like ER, MA, GASH, and then we use that to calculate the bias, standard deviation, and the mean square error. And then, as I said, we compare that with unadjusted value at risk. So the unadjusted here is just the simple quantile estimator of the observed portfolio return. That is, as you know, is given by this, and that's obtained from the empirical distribution of the observed portfolio return. So here, this one, it completely ignores the measurement error. So then we next use our approach, as I explained before, to estimate the adjusted value at risk. And for the truncation that I showed before, so we take L and K equal to 10. And then for the bandwidth parameter, we use the same one as in Utsu and Taylor. And so we consider, so there is a, so we use this rule of thumb, but for different constant here, so we take 1, 1.5, 2, 2.53, etc. And then we do the exercise for different sample size, so 125 and 500, and the number of replication is 10,000. So now let me show, so as I mentioned, 3 steps, right? I mean, so for the first one, where we compare the 2 estimators, assuming that we know the true distribution of the measurement error. Okay, so let me show a little bit the graphs, and then I have this summary. So, so what we see here, so either for ER and in the next table is MA1 and GASH. So what we see is that this is these columns here are for adjusted value at risk, and this is for unadjusted. So we have a bias, standard deviation, and the mean square error, and that's for different bandwidths. And we do that for different sample size. By the way, we also consider 250, not only this and this. And so what you see is that if you pick the right bandwidth, of course, here we use a rule of thumb, so we don't have an, we don't derive an optimal bandwidth, but we follow the literature on this. So what we see is that if you pick, for example, these two values for the bandwidth, that gives you a very, low bias compared to the unadjusted one. And also there is a huge improvement in terms of standard deviation. And of course, combining these two, you expect to have a better mean square error compared to this. And that's of course the case for, I think the comparison doesn't change when you improve the, when you increase the sample size. So again, you see that there is a, maybe there is some improvement. Okay. So what we see is that, again, the bias and the variance and the standard deviation are lower than in the case of, in absolute value than in the case of unadjusted one. So that's for ER1, and I think the picture is similar for MA1. So we consider, again, this is for 1%. The picture is similar, as you can see here. So you compare with this and for this group. Of course, if you have the wrong bandwidth, you may do less than the unadjusted value at risk. Okay, and then, for the GASH, I think is similar picture again. If you focus on these two bandwidths here, the picture is also similar. So this is again for 1%, but if you look at 5%, 10% that I'm doing in this here, again, repeating 3 different models for 10% again here, you see that the picture is quite similar. So sometime maybe, okay, so sometime maybe the bandwidth 2.5 is not working that great, but the 2.1 is always doing well. So that's what I'm summarizing here. For almost all DGPs, C equal to 2 or 2.5 lead to very significant gains in terms of mean square error over the unadjusted approach. And there is a huge improvement, even, like for bias and also the standard deviation. Now, for the case where we misspecify where we misspecify the distribution of the measurement error, so in the sense that the calculation are done under normality, but the true data is that the measurement errors are either simulated from a student with 5 degrees of freedom or from a mixture of normal. So again, so for example, so you can see it for ER1. So we have for ER1, for ER2, for GASH, we do it for 1%, but also for 10%, for 5%, etc. But if you focus on 99%, so what you see here is again a huge improvement. If you take again these two values, 2 and 2.5, huge improvement in terms of bias, variance, and mean square error compared to the unadjusted one. And I think that's the same for all the sample size. Again, you see it here. That's across all different models, I think. And even for GASH here, you see similar picture that even the unadjusted one is even worse. So that's what I summarize again here. So we find similar pattern to those found for the correctly specified case. So good degree of robustness for our proposed methodology for various deviation of the misspecification of measurement error. So again, these two values of the bandwidth, they work quite well. And then the last case is no measurement error case. So how our methodology behaves when there is no measurement error? So what, I mean, I'm going to summarize this here. So the performance of the adjusted and unadjusted approach when the measurement errors is not present. So what we find is that it's true that the unadjusted estimator generally lead to a smaller bias. But when the optimal bandwidth, when we pick again these two values used, the adjusted estimator has a much smaller variance. And that could lead to a better mean square error or smaller mean square error. Now for the empirical application, so we use high frequency data to calculate the value at risk of this five international stock markets, CAC, DAX, FTSE, FTSE MIB, and S&P 500. So yeah, let me show, I think I still have some minutes. So that's the results that we obtained. So, okay, so here we standardize the returns just for comparison reasons. So what we find is that the adjusted value at risk, 5% and 10%, is in absolute value is a higher. So if you do, for example, you compare 5% for the adjusted with 5% for unadjusted, what you see that the absolute value, or if you want the value at risk in absolute value is higher when we use the adjusted compared to the unadjusted one, and that's for 5% and 10%. So if you compare this one here with this, so what that means is that ignoring microstructure noise leads to an underestimation of risk, and I think that confirms the picture that we saw at the beginning here. Yeah. Right. So I think I'm done. So I'm just gonna conclude. So we develop a semi-parametric estimation approach for value at risk when the stock prices are contaminated with by measurement error. So we use Monte Carlo simulation to examine the performance of our approach in the presence and absence of measurement error. And then we apply this methodology to high frequency data to estimate the value at risk of 5 international market indices. Thank you very much. So I think I'm gonna stop here.
Thank you very much. Questions? Let me check if there's any questions on the chat. Or so from the audience, any questions?
I'm glad that everything is clear.
Well, actually, if we can go back to the point where you talked about kernels for kernels for smoothing the integral.
This one here?
Yes, here, yes. So why do we need kernels? Can't that be just used? Can't we just use the unsmoothed version? I mean, so this is the deconvolution result, right? So we could in principle just pick the f, the phi's, use this Fourier transform to just calculate it directly.
Yeah, that's a very good question.
Right? Or alternatively, you could have used kernel instead of an empirical density for x to start with, right?
You mean for this guy here?
Yeah, well, for this guy here to start with, yeah. So what I mean, why not use it?
That's a good question. So I mean, okay, I mean so we were at the beginning, we were ambitious to find an analytical solution. So I remember when we were deriving the results, so we were trying to to use that, to see if we can have some analytical expression for this, for the distribution function. Yeah, and I think that's the main reason. But I think also, I think we tried that without smoothing in the simulation, and the results were not that convincing.
Okay, I see.
Yeah.
And then
So
if you go even one page
this one here,
or maybe even earlier. So
yeah.
there's the observed R here. So this is the empirical characteristic function.
Yeah.
All right. So this is just the averages. I presume there are kernel versions of that, smooth versions.
Sure. Yeah. Yeah. No.
Well, right?
That's absolutely. That's what I mentioned at the beginning. We take the empirical one, but you can consider other kernel-based estimators. Yeah, I don't know. Maybe using that may save using this. So possibly if you use some kernel smoothing here, that may help. In terms of integral here, so it may help avoid using this one here. Yeah, we thought about this, but honestly we didn't investigate, because of course you have a lot of that involves a lot of calculations. I think we tried, but we was not that straightforward. Yeah, but it's a very good point. Yeah, this is a very good point.
Okay. Let me see if there are any other questions from the audience. Well, one other sort of question I had when I was listening to the point that you have a fatter tail with the measurement error, right? And of course, that translates into the properties of ValueatRisk and the lack of coherency and things of that nature, right? So so this is an important consideration, that you get a much fatter tail, right?
Yeah, yeah, that's what we saw here. With this simple example here, is that you can play with other distributions, but if you like, for this case, you see that the latent, if you want the convolution with normal and student, that leads to heavy-tailed, distribution. Yeah. This one here, yeah.
So in terms of coherence, the true latent, unobserved ValueatRisk coherence measure would be even more questionable. So it would be even less applicable to think about ValueatRisk in terms of coherence.
So I think you are talking. So okay, so you're talking about possibly like considering other measures here.
Yes.
Yeah. Yeah. I have to think about it, and yeah, I think because we deal with of course these measures, coherent measures. That depends also on the tail, right? And so certainly this will have an effect. So that applies also to the expected shortfall, right?
Exactly.
Because again, expected shortfall is an average, if you want. So you have an accumulation of when you estimate the value at risk, you underestimate it at all the points in the extreme tail. So we expect that will have more effect. For example, we expected shortfall.
Exactly.
Yeah. Which we do. I mean, we try to look at this now.
Yeah. Thank you.
My pleasure.
Let me see if there are further questions. Well, it's perfect timing. We're at the top of the hour.
It's okay.
So let me, if there are no further questions, let me thank Abderrahim, and
thank you very much.
We can send the speaker some virtual or not so virtual applause.
Thank you very much. Thanks a lot. So I see some old friends here. Igor, that I didn't see for a while. Hey, Igor. Good to see you.
Oh, wow. I haven't seen Igor for a while, too. I don't remember that style.
Yeah. Where are you, Igor? Where are you now?
I'm at HEC in Moscow.
Ah, right. So you moved from ETAM, right?
Yes, exactly.
Okay, good. Anyway, good to see you.
Yeah, it's nice to see you.
Thanks a lot.
Yeah, I was hoping that the recording would be off, but it's still on.
All right.
Well, we have to see if Alex can. It's probably good to turn it off. I'm not sure how to do this. I guess I could just stop. Stop record. I can see this. All right. Well, thanks for the record. Thanks, Abderrahim, again. I'm going to stop the recording now.
Thank you very much, everyone.